We're going to continue this week discussing supervised problems. Last week we talked about logistic regression. Now we're going to move on to the continuous version of logistic regression, linear regression. And in particular, we're going to use linear regression as a chance to think deeply about regularization and the types of regularization we can use and the influence that has on our optimization. So let's start with a standard linear regression problem. We're going to pose it like this. We're going to imagine that our distribution for our observed or our label y is going to be like this. Notice that y here is a single continuous value. So this looks just like in the logistic regression case where, but in that case, y was a binary variable. Now y is continuous, but still univariate. And we're going to imagine that y is distributed according to a normal distribution with this mean here and some variance sigma squared. Now note that this is a linear function of x. We take this vector and multiply it by x, and then also add a w0 intercept term to that. So this is a linear function. That's why we call this linear regression. Note that here we're in the discriminative rather than generative case because we're posing this as y is a function of x. Whereas you might remember last week we looked at some problems that we posed in the generative format as x is a function of y. But we're going to focus on the discriminative case this week. Let's look at how we can get our MLE estimate for our linear regression model. We've done this a bunch of times so far, so let's jump right in. So here we have our negative log likelihood, which again is going to be a function of w and sigma squared. So this is just going to be the log of that normal distribution. So we have a sum over our examples, and this is the log of our normal distribution Gaussian density. We can simplify this a bit. Note that all these terms here, these don't depend on n, so we can pull them out into this term here. And so this simplifies down to just this term here. Also note that we've plugged in here, we've defined y hat as just this product w transpose x. That's this thing here, just for simplicity of notation. So now notice that this second term just depends on theta squared. So if we're looking to optimize our w, the only term that matters is this one. That term here is sometimes called the residual sum of squares, which is, note that this is the same term here. We've thrown away the sigma squared factor and also this term here. So this we can write like this. Another way to write the same thing is as, so this is a sum over n. We can write this as in vector notation by the following. We've defined big X to be this matrix here, which is our n examples times d features, and the y vector to be n by 1. So this is the y for all of our examples. Now notice there's no sum over n in this expression here because we've done it over, because the sum over n is already captured within this matrix multiplication. So this term here is the same as this. We've just put, we've gotten rid of the sum by switching to this matrix notation. Okay, let's take the derivative of this thing. So the derivative with respect to w, note that we're doing this with respect to the entire w vector. We're going to be able to do it in one shot. We're going to take the derivative of this thing here. Let's expand it a little bit. It expands into 3 terms. We get one term that's the squared term, one term that's the y squared term, and one term that's the cross term, xwy. Note that when we take the derivative, the y squared term goes away because we're taking the derivative with respect to w. Then once we get the derivative, we get this thing, x transpose x w minus x transpose y. Now, so just to look at this a little more carefully, so x transpose is going to be a d by n matrix. X itself is n by d, so we multiply that by w to get a d-dimension vector. This thing is also going to be d-dimensioned because y is n-dimensioned. This thing is d by n. So we get a d-dimensioned gradient, which is what we want, of course, because this is a derivative with respect to a d-dimension vector. If we set this to 0 and solve, then we get this here. Then we can multiply by this thing, x transpose x inverse. We multiply on the left to cancel this out, and we get our maximum likelihood estimate, which is this thing. X transpose x, this thing inverse, times x transpose y. So this is sort of extremely widely used. This is called the OLS, ordinary least squares estimate, and it's a very nice way to get a analytical closed form solution to our linear regression problem. So closed form solution, no gradient descent required even. There are some practical considerations with this solution. In particular, with regards to this matrix, often it is not practical to do that computation. Often it's slow, and often this matrix here can be singular or close to singular, particularly kind of there can be numerical issues when it's close to being singular. This happens especially in the case where the number of examples, the number of training examples for the linear regression is less than or even only slightly greater than the number of features. So there are a lot of kind of numerical stability and better ways of doing this. We're not going to discuss those in this class. Most of them involve going through the SVD of this matrix instead of taking its inverse directly.